This video is meant to be a brief introduction of polyprotic acids. So by polyprotic, I mean any acid that has more than one acidic proton. So we could say diprotic or triprotic if we wanted to talk about exactly how many there were. But in general, the trends that I'm going to discuss apply to all polyprotic acids. So up to this point, we've mostly focused on what we call monoprotic acids, where dissociation leads to the production of a single proton and then a single anion. So this reaction with water would end here. So these are not going to continue on and further dissociate. There's nothing for it to dissociate to. And that's really obvious when you have a strong acid that is just a binary acid. But if you have something like acetic acid, which has this condensed formula here, so it looks like this, if you were to draw the line drawing. So it's the simplest carboxylic acid. And here, this is the only acidic proton. There are these protons here, but they're not acidic. And so this is still a monoprotic acid. So let's take a look at some polyprotic acids. Here we have sulfuric acid, and you can see that there are two acidic protons, and they are equivalent to each other. Each proton is bound to an oxygen. That oxygen is bound to a sulfur, and that sulfur has two double bonded oxygens and a single hydroxyl group. So this hydrogen and this hydrogen, they're both experiencing the same attraction to the rest of the molecule. Until one of them leaves, then there's a negative charge and there's more of an attraction. So you can think of it this way, where you have your sulfuric acid, and we'll say H2SO4, and it's going to dissociate into the proton and this compound here. And we can call this monohydrogen sulfate. And then what will happen is, as the pH continues to change, you'll end up getting this, and it has a little bit of an equilibrium. It's still pretty strong, 1.2 times 10 to the minus 2, but it's not strong in the sense that it's fully dissociating. And so that's what happens. So you produce more of the acid. So this process is what happens for all polyprotic acids. One of these is lost, and that changes the affinity that this proton has for the rest of the molecule. And so you can see from here that all of these protons in red, you can see that they're compatible, like they're pretty much the same. They experience the same attraction until one is lost. So it's not like this is always the first one that leaves phosphoric acid. Each one of these is equally likely to leave until there's a charge on here. And that's what these numbers indicate. By reporting three distinct or two distinct K values, what we're saying is the equilibrium for this first reaction is different than the equilibrium for the second reaction. So let's take a look at that. I'm going to use phosphoric acid as my example. So I've drawn it out here. I have a triprotic so definitely polyprotic here. I have a phosphate anion, and then I have 3 ionizable hydrogens, or 3 acidic protons. And you can see this is the oxy acid, where you have the proton connected to an oxygen, which is connected to something else. And so I can draw out the equilibrium of all of these acidic protons. So I'm pause the video and draw it out yourself and see if you get the right answer. And really you're just losing a proton at a time. So see if you can figure out what that would look like. When the phosphoric acid undergoes ionization multiple times, you start with the 3, and then you have 2 hydrogens, then you have 1, and then you have none. And so these all have different names, and this is usually called monohydrogen phosphate, dihydrogen phosphate, and trihydrogen phosphate. And then this is just the phosphate anion. And so each of these has their own K value because they each have their own equilibrium expression. So if you look at this here, this would be one of the equilibria. And then you would have another one here. And then you would have another one here. So go ahead and now write out the K expressions for these 3. So here are the 3 equilibrium expressions for the protons in phosphoric acid. And you can see that they are all fairly different. So this one, 7.5 times 10 to the minus 3rd, compared to 6.2 times 10 to the minus 8th. Remember that pH is a logarithmic scale, and if we're at to the negative 3rd and then negative 8th, that is quite different. And then negative 8 to negative 13. So we're talking on the order of 10 to the 5th different. And so it makes sense to think of these as stepwise. So if you had, for example, a phosphoric acid solution, and we told you that it had a pH of 2, then you know it's probably going to be this equilibrium that you need to use. Whereas if you have something that's closer to 7 or 8, it's going to be around here. And when we talk about buffers, we will talk about the relationship between Ka and pH on a lot more depth. But I just want you to start thinking about what it means to have this Ka value and what this actually means for these, right? So it means that our equilibrium is going to lie much further to the right. So we're going to dissociate a lot. And that means that if we wanted to increase the pH, that it would drive the reaction further to the right. So by adding some base to this goes away and this continues to dissociate. So as the pH increases, you see these things continue to dissociate. So that's really the idea behind polyprotic acids. And these are often important buffers, which is why I wanted to spend a little bit of time talking about them in some detail. So here's an example problem. We're going to look at carbonic acid. And I have sketched these here just so we can keep our vocabulary straight. Carbonic acid is a diprotic acid, so it counts as polyprotic. It has two hydrogens that are both acidic, and the first hydrogen dissociates to bicarbonate, and then this is lost to become carbonate. And so if you're having trouble remembering this, the bicarbonate can go both ways. So that might help. So here we have our pH of this solution. So we have a 0.050 molar solution of carbonic acid. Now, since I've told you it's of carbonic acid, what you're going to do is you're going to use these two in your equilibrium expression. And so you won't have to think about this one because we're just looking at some carbonic acid solution. So when you set up your ice table, you'll have your carbonic acid, your hydronium or hydrogen ion, and then your bicarbonate ion. You'll have your initial, your change, your equilibrium, and this is 0.050, and then we will lose X and add X over here. And then what we're going to need is our Ka value for the first dissociation of carbonic acid. So I look back at that table and I see that 4.3 times 10 to the minus 7 is the Ka for carbonic acid. And I can use my X is small approximation here. So I multiply this number here by 0.05, and then I take the square root of that, and I got X equals 1.46 times 10 to the negative fourth. And so I actually checked to make sure that I could use the X is small approximation, and I can, because when I take this answer for X here and divide by that, I get, and the percent is 0.2%. So it is completely valid to do. All right. So this means that my X value is here. And my question is to find the pH of this solution. So I'm going to write out my hydronium ion concentration is equal to 1.46 times 10 to the minus fourth. And remember that pH means take the negative log of H3O plus or H plus. So all I have to do is take the log of this, and it will be a negative number, and then it's multiplied by negative to get my pH. And when I do that, I get 3.83. So it's acidic, but not overly acidic. Now, say I had asked you to find the pH of a bicarbonate solution, then what you would have to do is use the Ka for this and use these two in your equilibrium expression and not these. So if it's a Ka, you're always starting with the protonated version on the left because it's an acid dissociation. So you want to see the formation of the hydronium ion and the conjugate base. If it's a Kb, it's going the other way. It is the base ionization. So you're going from a base that's either going to be negatively charged or neutral, going from negative to neutral or neutral or positive. So you want to make sure that you're paying close attention to how these are set up. So I'll show you what I mean by using ammonia as an example. And so if you have ammonia reacting with water to form the ammonium ion and hydroxide, this is a Kb reaction. This is a base ionization because ammonia is the weak base and we're showing the ionization of ammonia. However, you can have a Ka if you have the ammonium, because this here is a conjugate acid of a weak base, and that can react with water. And what that will make is ammonia and hydronium. And so just make sure that you're always paying attention to which equilibrium expression you've written out. The last thing you really want to pay attention to is how to solve for Ka and Kb. So we talked about Kw in class, and we said how that is equal to the Ka times the Kb. So at 25 degrees Celsius, that is always going to be 1 times 10 to the minus 14th at when it's in water at 25 degrees. So the Ka and the Kb just have to be a conjugate acid-base pair. It doesn't have to be water. Now, the Ka for water, for the hydronium and hydroxide, both happen to be 1 times 10 to the minus 7th. And when you multiply that together, you get 1 times 10 to the minus 14th. But if it's something like ammonia and ammonium, you can just plug those K values in and it will equal this. So anytime you are given a Ka or a Kb, you can very easily solve for the other one by using this relationship. So if you keep these things in mind, it should be fairly easy to work through more of these problems with some polyprotic acids.